And I knew exactly what to do, but in a much real sense, I had no idea what to do. In this video, I want to talk about really interesting properties of random variables and why they are so important. So as we saw in a previous video, a random variable is something that assigns to each element in our sample space a number. So something interesting you can do with a random variable, let's say we have a random variable y, is that we can then define many different random variables. So we start with y, and then we can define y squared, 3y, or any number multiplied by y, the exponential of y, if we want to. We can have the square root of y, and so on. Another thing we can do is that if we have two random variables of, of the same experiment, what I mean is that the simple events are the same. So let's say that we have x and y, then we can define many different random variables. For example, x plus y, x times y, power y. These are things that I haven't seen a use for them yet. Maybe when I study more, I will see something. We can also define 3x plus 2y, and we can change these two numbers, and so on and so on. So let's see certain examples of this. Let's take again the four-headed dice. By the way, if you don't know, a four-headed dice will look something like a pyramid. So you see three faces on top and one face on the bottom. Then we can get not the face up, but let's say the corners. So we can have a corner with the symbol circle, a corner with the symbol X, a corner with the symbol square, and a corner with the symbol triangle. So we have 1/4 of probability of having each symbol. And our sample space is, if we have the square corner, the X corner up, the triangle corner up, or the circle corner up. For each element of this sample space, we can assign a number. You can do it arbitrarily, and depending on the number you choose is one random variable or another random variable. So for circle is 0, for triangle is 1, and for x and square was 4. This was the random variable we used in the previous videos, but we can use a different one. We can also assign to square 1, to x 2, to triangle 3, and to circle 4. So now I will call this random variable set. So if this one is x and this one is z, we can have here we sum two random variables that are from the same experiment and from the same sample space. But what happens if we want to sum two random variables of different experiments? For this, we have the following example, which will illustrate what we have to do. We have a 50-cent coin and a €1 coin. We do two separate experiments, flipping this coin or flipping this coin. The outcome or the simple events for this experiment of flipping this coin here will be having the head of the coin or having the tail of this coin. For this other one, we have having the head or having the tail. They are different coins. So these are different in a priori different experiments. For head, I will put 1, and for tail, I will put 0. For head, I will put 1, and for tail, I will put 0. A priori, I cannot sum these two random variables because they are from two different experiments. But we can have a combination of these two experiments and say throw the 50-cent coin and the 1-cent coin. And now our experiment has grown. We have the head of 50, head of 1, head of 50, and tail of 1, tail of 50, and head of 1, and tail of 50, and tail of 1. And now this is all my new simple space. Now, y, which was the one here, will give us 1 in this case, that is head of the first coin, and 0 for the rest. Let's put here again 50. And now this second experiment, the set, will give us 1 for the head of the €1 coin. So here give us, and now we can sum y plus z. And that will give us, so a priori we cannot sum these two random variables, but then we can modify the experiments and then sum the two random variables. And this is quite abstract and not so easy to grasp. And I think most of the classes of statistics takes this for granted. I hope you understand it. You have to sit, think, and rethink about this in order to understand. Now, I'm telling you this because there are properties for the mean that I can only explain if you understand this first. And if I just put them there, like many statistical books, I feel I am cheating and I am not explaining it well. Also, I needed to sit down and understand what that means. So the property is that the expected value, or the mean, is linear. And what linear means is that if I have, for example, here, we have two random variables. Let's start from there. We have x and y, random variables of the same experiment. As I say before, the experiment can be expanded. So in the end, we can sum any two random variables, but we take of the same experiment just to have inner peace in our minds. So the expected value of, let's say, a number times x plus another number times y, that will be equal to 3 times the mean of x plus 4 times the mean of y. This is what linear means. For the case being, let's take this for granted. I mean, not necessarily with 3 and 4, no, right? With anything, we can just put here two numbers and here any number. In fact, I think it's easier to prove it like two separate statements, and then these two together will give the one I'm given on the top. C is any fixed number. For example, C can be equal to 3, or C can be equal to 4, or C can be equal to anything. And because it's true for x, then it would be true also for y, or for any random variable that is from the same experiment. So another thing I want you to understand about random variables is that note that flipping a coin of 50 cents, that experiment is really similar to the experiment of flipping a coin of 1 cent. They are different experiments, but they run the same way. As the example of these two coins, there are many different probability experiments that are similar, and then we classify them under the same name. And to study it, we only see is a random variable with its probability distribution. So flipping of coins, any fair coin is described with 0, 1 as the random variable and 1/2 as the probability function. Not only any fair flipping of a coin, but any fair choosing over n things, of n numbers. n things. It's described as we have the first thing, the second thing, the third thing. So here below is a random variable that to each event we assign a number, being like the first, the second, and so on, number 1, number 2, and so on. And to each number we assign the probability of 1 over n. This kind of random variable together with probability functions are called uniform distribution. We will see in the next videos more examples of random variable plus probability functions that describe a big variety of examples of experiments and sample spaces. And here we will have an index of how we will see them. First, the binomial distribution. This one is about the number of success in n trials. The second one is called the geometric distribution and is the number of trials for one success. Then we have the negative binomial. I have no idea why they give it these names. Well, the geometric I know, the binomial I know, this negative binomial I have no idea. But this one is the number of trials for R successes. Then we have the hypergeometric, and this is also the number of success in n trials, but the difference between this one is that each trial is independent, and in this one the trials are not. And the fifth one is the Poisson distribution, that is the number of success in an interval of time. Hope you enjoy. See you next time, Probability Buddy.